Hello everyone. Welcome to my presentation on high accuracy RF-PUF for EM security through physical feature assistance using public Wi-Fi dataset. I'm Mohammad Faizul Bari. I'm a PhD student in the Department of ECE at Bari University. Let's start our presentation with the outline of this talk. I'll first talk about the challenges that I'm going to address. Then I'll discuss about physical signature-based authentication. I'll describe the whole experimental setup and dataset. I'll try to explain why RF-PUF is superior. Then I'll show some results and discuss about them. And finally, I'll conclude my talk with a brief summary of the whole work. Okay, so the challenge, the RF security. So Cisco predicts that by 2025, there will be around 75 billion IT devices, and these devices are resource limited in terms of power and area, and they're exposed to wide attack surface because most of the time they're mobile and they're employed in remote places. So they're the weakest point of the whole large network they're connected to and define the security of this large network. And security failure of these devices can have a catastrophic or awful consequences. So the traditional methods for IT device detection, IT device authentication is digital signature-based methods. So we have several methods. For example, here symmetric key and asymmetric key cryptography, where secret key is used for encryption and decryption purpose. The only difference between these two is that symmetric key uses same key, whereas asymmetric key uses different keys for encryption and decryption. Another method is multi-factor authentication, where user uses a unique password. Along with that, another factor used, that is biometric fingerprint or a secure app or some other method like secure device, something like that. So these two or multiple factors are used for authentication purpose. That's why it's called MFA or multi-factor authentication. Another method is open authentication or OAuth. So what happens in OAuth is that the resources are located in a remote server, and there is an authorization server. So the authorization process is separated. So the user gets his or her resource through the client app. So what happens is that the resource owner, the user, grants access to the authorization server, and the server then sends an access token to the client app. The app can then fetch data for the user. Okay, so let's talk about the problem of the vulnerabilities of the traditional methods. So first and most important is cross-site request forgery. So what happens here is Alice is our user and also the victim who logs into the server, and the server, since he or she has the valid token, since he or she has the valid credential, the server sends a valid token. Now, Melody, the hacker, sends a forced request that looks like a real one, but actually a fake one. Alice unknowingly forwards the request, and since Alice already has the valid token, the request is executed and the security is compromised. Another method is brute force attack, where the attacker uses automated tool that uses different combination of password or secret key. And the weaker the password, the higher the probability of getting hacked. Another problem with digital key-based authentication is that sometimes you need manual verification. For example, open authentication or multi-factor authentication requires the user input. So that's cumbersome for a large number of devices. Okay, to address these issues of digital signature-based methods, there is another method called physical signature-based authentication. So what physical signature is really? So there are device-specific unique properties. So during device fabrication, due to manufacturing process variation, non-linearity of various components like power amplifier and to digital converter, or bandwidth limitation of filters, all these can contribute to these unique properties. So they're manifested as unique system-level non-idealities, and these RF non-idealities are used for RF device fingerprinting, as can be seen here. There are several RF fingerprint-based device authentication methods. We'll primarily talk about two methods here: deep neural network or CNN-based Oracle method, and then RF-PUF method. So let's talk about Oracle first. So This is the whole diagram of how Oracle works. So IEEE 802.118 standard frames are generated from MATLAB. They're fed into a transmitter, which is USRP radio and USRP X310 radio, and then that data is received to a receiver, which is USRP B210 module. And this raw data is then fed into a deep neural network, which actually is a 1D CNN that looks like AlexNet. So the CNN structure is shown here. As you can see, this whole structure is divided into 4 sub-blocks. Each block contains one convolutional, 1D convolutional layer that has 1/7 sized filter, 128 filter of them. And then another convolutional layer, but with a smaller filter size, 1/5. It also has 128 filters in it. Then we have a max pooling layer. So this is the sub block, and 4 sub blocks forms the main chain. Then we have fully connected layer of 256 nodes and another fully connected layer of 128 nodes, and finally softmax output. Another approach is RF-PUF, where similarly we have this frequency offset IP0 and PA nonlinearities, all those RF nonlinearities in the transmitter. The data is transmitted and received to a receiver. But instead of feeding that raw data to a CNN, what RF-PUF does is it processes the data. So the noisy signal is processed by framing and averaging so that the noise is reduced. And then a proper feature set is selected. So here, CF or carrier frequency offset and IQ data, which are RF non-idealities, they're used. IQ data are actually combination of, or it contain information about various non-linearities, non-idealities, such as phase error or magnitude attenuation, etc. And also it uses coefficient of frequency offset variation, or COV, which is a statistical parameter derived from CFO. So all these selected features and or finely tuned features actually help us neural network to provide more accuracy. And RF-PUF has an edge over Oracle, as we'll see in the result section. But first, let's talk about the experimental setup. So this is the conceptual setup. The experiment was done by Kunal Shankhe and others at Northeastern University. The dataset is available publicly in their website. So here you can see that USRP X310 SDR is used as receiver, and B210 SDR is used as a receiver. And the transmitter transmits IEEE 802.11 standard component frames. So these data are generated in MATLAB, and also the received data is also collected in MATLAB. The actual setup looks something like this. A room of 50 feet by 70 feet was used, and the transmitter and receiver was kept at a certain distance. So this transmitter receiver separation has been varied from 2 feet to 62 feet in 6 feet steps in between. So this is the brief description of the data set. So we have data from 16 USRP X310 as transmitters and 1 receiver. We have TXRX or transmitter receiver separation varied from 2 feet to 62 feet in 6 feet step. Then data processing. So Oracle doesn't have data processing. So when I'm talking about data processing, this part is solely from RF-PUF. So data grouped into 1,000 frames from each transmitter. Each frame contains 2,560 samples. Carrier frequency offset calculated from each frame, and coefficient of carrier frequency offset variation, or COV, which is basically the ratio of standard deviation and mean of carrier frequency offset, a statistical parameter. Then carrier frequency offset and IQ samples in 4 quadrant are used as features. So in combination, there are total 10 features. So we show our result in 2 cases, static and quasi-static. So by static, we mean that the separation between transmitter and receiver is fixed. That means we have a fixed channel length. But for quasi-static, the separation can vary, as you can see. So the channel length varies. We have seen that both static and quasi-static, both in static and quasi-static cases, RF-PUF outperforms Oracle. You can see that in static cases, RF-PUF shows 100% accuracy compared to 98.6 in Oracle, and for quasi-static cases, RF-PUF shows 96% accuracy compared to 87.1 in Oracle. So RF-PUF performs much better compared to Oracle. So the question is, why RF-PUF performs better? So Oracle uses only raw data samples, and these data are contaminated with noise and interferences. So their CNet does all the heavy lifting, and due to absence of people's in it, cannot use the full potential from the data. On the other hand, if we use only statistical parameters, the training process tend to fit the model towards those parameter values. So it leads to overfitting. So RF-PUF takes a middle ground. It processes data to reduce noise and uses both RF non-idealities and statistical parameters as feature. So RF-PUF has an edge over Oracle, as can be seen from the result. Okay, now let's discuss our results in detail. So first we'll show the accuracy of RF-PUF for static channel. So we have shown our accuracy with respect to transmitter receiver separation. As you can see here, the accuracy is around 100% up to 38 feet, except one outlier here at 26. This point, the outlier at 26, it is consistently available in all the figures, as you will see next. So we suspect that that might be something from the data, but nonetheless, we have 100% accuracy up to 38 feet and more than 95% accuracy in the whole range. So 2 feet all the way up to 62 feet. One interesting thing here is that we need a lightweight neural network for this. Here we're using like one hidden layer and only 20 layer in that layer, or only 20 neuron in that layer. Next, we'll discuss the accuracy of RF-PUF in quasi-static cases, but we'll discuss it in terms of two important design considerations, that is neural network architecture or neural network parameters and data volume. So first, let's talk about neural network parameters. So you can see the accuracy with respect to number of neurons per layer, and it's increasing from left to right. Also, now as we increase the number of hidden layers from bottom to top, we see the accuracy also increases. So we can say that the accuracy increases in both cases if we increase the number of neurons per layer, that is the width of the network, or if we increase the number of hidden layers, that is the depth of the network. Then we have shown that the effect of data volume, as you can see here, we have varied the sample percent from 2,560 to 3 times, 7,680. We see that accuracy also increases. So the more data means more information, and the feature values are more concrete, and the accuracy improves. Okay, next we apply RF-PUF problem. Next we apply RF-PUF to clustering problem. This is important for self-listing devices. Here we'll do binary clustering. That means 2 cluster, authorized and unauthorized group. So what we do is we randomly assign devices into authorized group and unauthorized group. Authorized group has 10 devices and unauthorized has 6. We tested for both static and quasi-static cases, and we also reported false positive and false negative values because in some application that might be useful. Okay, now let's see the plot. So we see that the accuracy with respect to transmitter and receiver separation is greater than 95% throughout the range, except that outlier at 26 feet. And the false positive and false negative rates are less than 2.5% in throughout the range, except that outlier. So it's pretty good accuracy throughout the range. Next, we show the clustering accuracy for quasi-static cases. As you can see, the accuracy has dropped slightly from 95%. Now we are getting around 90%, and in some cases slightly below that. But the performance can be improved using more data or increasing the model capacity of the neural network, as we have seen earlier. Okay, to summarize the whole work, on the same data set, we have applied RF-PUF and Oracle, and we have seen that RF-PUF performs better than Oracle in both static and quasi-static scenario. We have seen that 100% accuracy can be achieved all the way up to 32 feet, and more than 95% accuracy for the whole range from 2 feet all the way up to 62 feet. We have seen the effect of data volume and neural network model capacity, and we have seen that increasing those increases the accuracy. We have also applied RF-PUF for binary clustering, which can be used for self-listing devices. We have seen that in that case, we can gain 95%, more than 95% accuracy for static case or static channel, and more than 90% accuracy in quasi-static case. To summarize, the advantage of RF-PUF is that RF-PUF gives you a better performance without any additional power overhead or without any modification to the transmitter whatsoever. So that's all about my presentation. Thank you for listening.